So today we're going to talk about the last two tests that we will use to test whether our series is convergent or divergent. So the first test is the ratio test, and then we're going to talk about the root test. So a ratio test provides a way of measuring how fast the terms of a series is approaching zero. So that's why we're going to use the limit to determine whether my series is convergent or divergent. So let's see. I have a series of an, all non-zero. To use the ratio test, you're going to take the limit of an plus 1, you divide it by an, and see what value you get. So it's pretty easy. You just calculate the limit. Depending on the value of the limit, you're going to determine whether your series is convergent, divergent, or if you don't have enough information. So let's see. If the limit, let's call it rho, if the limit is between 0 and 1, then the series converges absolutely without doing anything else. If the rho is bigger than 1, so if my limit is bigger than 1 or equals to infinity, my series is divergent directly. And the only problem with the ratio test is if I got the limit to be equal to 1, then we don't have enough information to determine whether my series is convergent or divergent. So I need to use other tests or other techniques to test the convergence. Okay, so before we start doing some examples, let's review what it means for something to be factorial. So if I have n factorial, it means that I'm multiplying n times n minus 1, n minus 2 up to 1. So we keep subtracting 1. So for example, if I have 5 factorial, this means I have 5 times 4 times 3 times 2 times 1. How about if I have like 2n factorial? So 2n, you take 2n, then you keep subtracting 1 from every term until you get into 1. So the ratio test is very useful when we have either factorials or we have exponentials. So if I have exponents, if I have factorials, then I always think about I might need to use the ratio test to solve the convergence of a series. So let's see these examples. Let's start with number 1, where I have the summation of 5 to the n over n factorial. So here I have a factorial, I have an exponent, so the ratio test might help. So now my an is 5 to the n over n factorial. My an plus 1, you just add, you substitute n plus 1 instead of n. And now we're going to divide an plus 1 over an. So now I have the limit of 5n plus 1 divided by n1 factorial, n plus 1 factorial, over 5 to the n over n factorial. Now here, we're going to use the keep change flip rule since we're dividing two fractions. So that's the limit of, to keep the first one, you turn the division into a multiplication, and then you flip the second fraction. So that's n factorial over 5 to the n as n goes to infinity. Now if you can see here, I can do some cancellation. 5 to the n divided by 5 to the n is 1. And here I got 5. Now n factorial, so this is n plus 1, n minus 1, up to 1. But this part here is just n factorial. So you can turn the n plus 1 factorial into n plus 1 multiplied by n factorial. So I can cancel the n factorials and I only get n plus 1. So once we simplify, we're going to have the limit of 5 over n plus 1 as n goes to infinity. And since n is positive, I don't have to put the absolute value there. Now if you solve the limit, this is just 0. Okay, so let's review. We have the ratio test. I calculate this limit. And if I get a value that's less than 1, then by the ratio test, the series that we have converge absolutely. And if it converges absolutely, then it must converge. Okay, so that's it. Let's see the second example. So my a of n is everything that's inside, and now let's divide. I'm just gonna substitute n plus 1 instead of n, and then I'm gonna use the keep change flip rule, So we're going to multiply by the reciprocal. Right, we have here. This is 2n factorial over -1 to the n factorial. So this is my an plus 1, this is my an. Okay, let's see how we are going to simplify. The negative with the negative, so I have a -1 here, but since we have an absolute value, then that goes away. Then n factorial with n plus 1 factorial, we get n plus 1. Now let's see for the denominator here. This is going to be 2n plus 2 factorial. If we want to cancel it with the 2n factorial here, let's rewrite it. So this is 2n plus 2, then we subtract 1, so plus 1. Then if we subtract 1 again, we're going to get 2n, and we're going to reach 1. So this is just 2n factorial. So I can cancel this with this part, and I have this in the denominator. So now we have the limit, and I can cancel the negative with the absolute value. And since n is positive, I can remove the absolute value. And now, since the power or the degree of the denominator is bigger than the numerator, then I'm going to get a 0. Because you can try using L'Hopital's rule. Now again, this is less than 1, then converge absolutely. And now for the last example, I have my an to be n squared over 7 to the n. So let's apply the limit. We do an plus 1 first, then multiply by the reciprocal. Now let's simplify. This goes away. I have a 7 here. And technically these I can't like cancel them directly. But here I'll have like n squared plus 2n plus 1 over n factorial over 2n squared as n goes to infinity. Now here you can either use L'Hopital's or take the coefficient of the highest exponent, so I'm going to get a 1. Oh, sorry, I forgot the 7 here. So I got 1/7. Now, since this is less than 1, then converge absolutely. So that's it. You take your a of n, you take the limit of an plus 1 divided by an, and it's a bunch of like a cancellation process and evaluating limits. Depending on the value that you get, you determine whether it converges absolutely diverse, or if we need more information, or if we need to use like a different test. And like I said, the ratio test is usually used when we have factorials or exponential, because it's kind of difficult to compare or use comparison tests and stuff like that when we have factorials and exponents. So that's why it's better to just go to the ratio test directly and see if that works. Okay, so now the second test for today and the last test for this chapter is the root test. The root test is useful when we have an exponentials, like if I have an exponent of degree n. Let's see why it's useful to have a degree n. So here, we're going to take the limit of the square root of n of our series, or what's inside of the series an. So here, if an has an exponent of n, I can easily cancel it out with the square root, with the root of degree n. So that's why the root test is useful when we have a degree of n. So as we did for the ratio test, we take the limit. Once we get the limit, depending on the value of the limit, we determine whether our series is convergent or divergent. So if it was between 0 and 1, then the series converges absolutely. If it was bigger than 1 or infinity, then the series diverges. If it's equal to 1, then we need more information or we need to use a different test. So let's see these examples. if I have the summation of n squared plus 1 to the n over n to the n. So this is my a of n. Now we can rewrite this as n squared plus 1 over n all to the n. So here, if we take the limit of the nth root for the absolute value of our an as n goes to infinity, now the square root of an is just positive, so we can, not the square root, the absolute value of our a of n, because it's positive, it's gonna stay the same. And then I have the square root of n and an exponent of n, so I can just cancel them together and get the limit of n squared plus 1 over n as n goes to infinity. Now if you apply L'Hopital's, or you take the, you'll see like, oh, my degree in the numerator is bigger than the denominator, so this is infinity, which means by the root test our series diverge. Oh, it's already here. So yeah, the series diverge. Now for the second example, let's rewrite our a of n as 1 over n plus 1 all to the n, because 1 to the n is always 1. So we can have like an exponent 1 here and just combine it into 1. And then if we take the limit we can cancel the square root of n, not the square, the root of n with the exponent n. And we're going to have the limit of 1 over n plus 1 as n goes to infinity. And if you plug in infinity, you're going to get a 0, which is less than 1. So by the root test, this series converges absolutely. Okay, so that's pretty much it. You take the limit. Depending on the value, you determine whether it converges or diverges. So that's the last of chapter 5. I'm going to upload another video comparing all of the tests and showing you how to choose which test to use when you have a series, and how to solve like conversions in general. I'll just do a bunch of examples. But for now, this is it for chapter 5. We have these suggested problems if you want to do extra practice, and you can start Lumen Homework 5. You can do problems from 1 to 3. If you have any questions, please email me, and best of luck.